All right, good morning, and all right, good morning, and my apologies if you are out there and went over to the channel that I'm supposed to be on, which is the Southern Space Rocks, but for some reason YouTube is not allowing me to broadcast through that this morning, but it is allowing me to broadcast through my other account, which is Georgia Craters. And so I hope you join me here. I also will have this posted back on the Southern Space Rocks channel as soon as it will let me. But again, I'd like to welcome you to this renewed edition of the At Home Planetarium show. And I'm going to now take us away to the night sky this evening. We're going to see what's out there for us to enjoy, and then we're going to take a bit of a tour through part of our solar system today. And we have this set here for the Atlanta area. The sky across most of the United States would look similar, though. We're not that different from place to place. But as we look out after sunset, this is right now set at 8:18 p.m. tonight. Just following the setting sun, looking off to the west, we see the planet Mars that we'll examine more closely as we go through the morning. But if you have a very low horizon, you might be able to catch Mars there in the setting sun. And above that, you will see the very bright Arcturus. And Arcturus is the brightest star in the constellation Boötes. And Boötes looks a bit like a kite here. It's actually the herdsman. And we'll turn on the constellation artwork here so you can see how the ancient astronomers of Greece and Rome and other cultures saw some of these figures there in the sky. You'll also notice around to the northwest the Big Dipper. And one of the ways to find Arcturus or to find the Big Dipper is look at the tail of Ursa Major, the giant bear. And you can form an arc there with the stars of the tail that arcs over to Arcturus, is what my astronomer friends often say. And as we come up a little bit higher in the sky, I want to draw your attention to this large swan here, Cygnus the swan. We have an eagle here, Altair. And if we look a little bit below that to the west, we will see a lyre there, the musical instrument, and the bright star Vega, which is one of the brightest stars in the nighttime sky. Very bluish star to your eyes, bluish white. And I'm going to take the artwork away and the constellation markers away as well. And hopefully your eyes are drawn to this triangle there in the sky. If it's not, we'll go back to the constellation markers just for a moment. Then we see the outstretched neck and the wings there of Cygnus the Swan, and the bright star Deneb there at the end. Altair is the eye of the eagle there, and then we have Vega there at the bottom. So this is what my astronomer friends call the summer triangle, and it holds on for much of the autumn months before finally sinking out of our nighttime view in the early part of the winter. But I'm going to turn the constellation lines there off for a moment and bring us back down to the horizon. Again, we see the back and the tail of Ursa Major, or the asterism we call the Big Dipper. As we swing around to the southwest, we can catch our moon here in its waxing gibbous, sort of transitioning from crescent to waxing gibbous here. And that bright star very close by, that, as you see, is Antares. Very, very red star. This is a red supergiant, and it is the the brightest star here in Scorpius, the Scorpion. See, what I often see is the outstretched claws here of the Scorpion. You can follow the body through the moon tonight, and it comes around into the stinger at the end of his tail. Again, if you can't see that, we can put those up. And I sometimes see that as kind of a flower there in the sky. But as we follow around to the singer, just across the way is the tip of the arrow of Sagittarius the Archer. And right in this area, right in between them, we'll go back and take the artwork away. And this is where you will find the very center of our Milky Way galaxy. And in our bright sky here in the Atlanta area, may have a little difficult time seeing the Milky Way, but you see the sort of milky stained band across the sky here that goes up through Deneb, through Cygnus the Swan. In fact, one of the ways that you can know you're looking in the right place to see the Milky Way, even if you're in a light polluted sky, is to follow the outstretched neck of the swan off to the south, and it will be following the Milky Way, the outer bands of our galaxy as seen from Earth, and it will come right here in between the tail of the scorpion and the arrow of Sagittarius. And this is the area right toward the core of our galaxy where there's a feature that astronomers call Sag-A star. Sag-A star. The star is not a star; it's an asterisk-like star, and that is the way they denote the black hole at the center of our galaxy. One of those supermassive black holes that often hangs out at the center of galaxies. We're going to swing around a little bit farther to the southeast and see what we can find there. We still see Altair, but as we move around over to the southeastern sky, we'll see Saturn here in the early evening. And you actually might be able to imagine then an arc across the sky here, and the search window comes up there, but Saturn is sort of connected over to Mars and our moon by an arc across the sky that we call the ecliptic. That's actually the equator of our solar system projected on our sky. And we can see if I can get that up here. You can follow that arc, and that's where you're going to look for most all of the planets and even many asteroids out there in our sky. And as we move around here to Saturn, I'll give you a little bit of a close-up view. We'll get a much closer view a little bit later. Can actually pretend that we're looking with our telescopes, and you're not going to see this view. This is a spacecraft view. But right here is Titan. And Titan is large and bright enough for you to be able to see with a telescope. If you have a good telescope and you see a bright thing very close to Saturn, you might find Titan. Enceladus is small but extremely bright. One of the brightest things out there in our solar system. It's like a completely ice-covered world. And that may show up a little bit off to one side of Saturn tonight. And Dione is another ice-covered moon there of Saturn, and it may show up as well. Rhea is a little bit larger, so this is a great opportunity for you to actually focus to see if you can see Enceladus, Dione, and Rhea. Again, look very close to Saturn for Titan. A few nights ago, Titan actually had a transit across Saturn, and so some astronomers, particularly our amateur astronomer friends, took fantastic photos of not only Titan almost floating above Saturn, but actually the shadow cast of Titan on the cloud tops of Saturn. So I'm going to come back away from our close-up view there. Your view may be through a telescope, maybe a little bit more something like that. You just see a little bit of the elongation where the rings are of Saturn, but then look for those moons out there around it. So I'm going to move back here to, you also will notice that Neptune is nearby. That's going to be something you're going to need a pretty good telescope in order to see. And we'll go ahead and swing around to the northeast. And if we put our constellation markers up again, we will notice that we're looking at a gigantic square in this part of the sky, and that is the giant square of Pegasus, the mighty flying horse. Put this up here, and you also see then nearby the figure of Andromeda. If you can find the great square Pegasus and find the stars leading off to the northeast, and look just here in this region of her outstretched arm, you may have an opportunity to see our nearest spiral galaxy neighbor, and that is the Andromeda Galaxy. It actually occupies a region in our sky that is slightly larger than a full moon, but it is much, much further away, much fainter. But if you have a good telescope, you might be able to make out the fuzziness there of the galaxy. And if you're able to take photographs with a good telescope, then you can actually get really spectacular images of the spiral arms. So that's where I'm going to end those features of our nighttime sky for now. And if you did manage to make it over to this and have any questions, even if you have questions later in the recorded version and want to put those into the chat, feel free to do that. But for now, I'm going to stop sharing for a moment that program, which is called Stellarium. And now I'm going to go over to a very special piece of software called OpenSpace. And this is something you actually can download and use yourselves, but I'm glad you're here with me for a little tour through our celestial neighborhood. And what we're looking at now is not a planet. It looks like a planet, but this is actually a map of the cosmic microwave background radiation, as they call it. It sort of maps out the edges of what we call the observable universe. And it's 93 billion light years across, expanding out very fast. And as we dive in, we start to see the products of one of our sky surveys, the SLEW Sky Survey, and it's showing us each one of these is not a star but a galaxy. And so we see many, many galaxies out there, and as we zoom in, we start to see our own galaxy come into view. Of course, this has to be an artist rendition. This is the one galaxy we can't see from our vantage point, but we infer from the positions of the stars that we have these spiral bands. And we're located sort of in the middle to the outer portion of the Milky Way. And you'll see there as we dive into the plane of our galaxy, now we start to see individual stars, and we have a lot of space between them initially, but now we start to see stars that are much closer to us in what we call the local group. And if you could see each one of these denoted, you would see some of the ones that form our constellations. But there in the distance, we see the glow of our sun. That's what it would look like if aliens were visiting our solar system. You would see the bright glow of Sol, our sun, before being even aware that you were part of a planetary system. And as we approach, we have the software configured so that it will show us the orbits of our planetary neighbors. And as we come in here, we would be out in a region initially in the Oort cloud where our comets linger. And here in this region, we would start to encounter those icy objects that we call Kuiper Belt objects. Icy worlds, many of them round small planets like Pluto, but many also just scattered lumps of ice. But here we start to see the orbits of our traditional family of 9, and I said 9. For planetary geologists, Pluto is a planet. And in fact, we have 110 planets in our solar system because we consider planets those objects that they're spherical, or in what we call hydrostatic equilibrium. They obviously go around a star, but then they also have enough mass not just to be a sphere, but they have enough mass to have heated up and separated, or what we call differentiated, and that then creates layering, like our own Earth with a core and a mantle and a crust. and that drives geology. And I'm actually going to have us start out here this morning at Pluto. And let's go ahead and do this again as you were an alien adventurer coming into our solar system for the first time. You would encounter the ice worlds of our outer solar system, along with our ice giants of Neptune and Uranus, our two gas giants that also we think down deep have a lot of icy material. Here you see the orbits of not just Pluto, but its 5 moons, and one of those is very special that we'll look at in a moment. But let's go ahead and look here at the orbit of Pluto. Here you see the orbit around the Sun, but you'll notice that it does something kind of interesting in that as it goes around the Sun, it also is going around a point in space. And that's a little different than our other planets. Because our other larger planets, they orbit a point inside of themselves. Pluto actually orbits around a barycenter, as we call it, that is offset outside the planet itself, and it actually goes around a point that is shared with its neighbor Charon. And we'll see Charon in just a moment, but from our viewpoint then, because it's going around this point outside the planet, Pluto wobbles. And as we then dive in here closer to see the imagery of the New Horizons spacecraft that flew back in 2015, one of the features that we'll see is this region called Sputnik Planitia. It is a large impact basin that is low and filled with ice. Around it, you see icy crust that is made of water, mostly water, like we find in your freezer at home. But this area, instead of being H2O ice, is nitrogen ice. And the nitrogen actually can sublimate away from this. And in the warmer periods, when Pluto is at the closest point to the Sun, and Pluto will have a thin nitrogen atmosphere. But in its colder times, it will freeze. And actually, most of the time, most of the nitrogen here is frozen down in this basin. And we see effects, though, of it warming up and sublimating by this sort of thumbprint terrain, as it's called, on the surface. These ridges are the result of sublimation of the nitrogen ice. But we also see these polygons, these multi-sided shapes here on that surface, and we believe that those are the result of convecting warm liquids or slushes underneath. Going on today. This is an active world, and around the edges of this basin, some of that convecting material seems to actually erupt out and form ice volcanoes, what we call cryovolcanism. And so Pluto, again, is a very, very active world. There are times that it may actually be able to rain or snow, or at least extrude liquids onto the surface. They wouldn't last very long in this thin atmosphere. But some of these valleys and fracture-like features here that you see, if you look carefully at them, some of them look sort of curved, and they're regions that look almost like dry lake beds. We think that these are either, or possibly both, times when both liquid methane, what you call natural gas, CH4, that it can be a liquid on the surface for brief periods of time, as well as perhaps liquid nitrogen, the liquid equivalent of this frozen ice here, or the thin gas in the atmosphere. Nearby to Pluto, as I mentioned, is its companion planet here. This is really a double dwarf planet system, and I'm going to go kind of flew through Pluto there for a moment and see Charon on the other side. One of the striking features of Charon is this dark region at its north pole. This is what the New Horizons team calls Modor, after the Lord of the Rings location. And this dark material actually appears in reflected light as a reddish color, composed, we believe, of the chemical compounds called tholins that develop as hydrocarbons, carbon, hydrogen, the basic building blocks of organic molecules. When those are bombarded by UVA radiation from the sun, they turn a reddish color, they darken, and we believe that this material might have originated on Pluto by eruptions on Pluto, or maybe even impacts on Pluto, throwing material out to space, settling there on the North Pole of Charon. As we look at other parts of the surface, we see a number of impact craters, actually lots of impact craters in places, but also smooth areas indicating relatively young surfaces. We see some large craters like this basin here. This is called Dorothy, after Dorothy Gale, the Wizard of Oz, because features on Charon are named for great explorers of science fiction. So, and both authors and explorers of science fiction. On Pluto, the features are named for both human and robotic explorers, like this first artificial satellite, Sputnik, there in Sputnik Planitia. Those are, again, named for real explorers, not fictional. As we come in a little closer, we see some areas that have a lot of texture to them, and there's some thought that these may almost function like glaciers here on the surface, that there's evidence of movement. And in some of the valleys, you actually see sort of icy landslides. And it's been proposed that some of these lobate structures are cryolava flows, and so possible evidence of volcanism even on this small, tiny, icy world. So next we're going to head over to the ice giant Neptune. Like our other gas giant planets, Neptune is largely made of hydrogen. But as you go deeper into it, the pressures increase, and the temperatures change, and the composition at this area of our solar system is a little different than places like Jupiter and Saturn. So we think that underneath this is a lot of nitrogen and base material, including ammonia. And we may have ammonia ices and slushes down deep. And it's even been proposed that some of the hydrocarbons here could actually be under enough pressure to form diamonds deep inside of Neptune. Can you imagine, literal raining diamonds out of the sky? Of course, the entire world here is really sky, and we see some of the storms here, like the Great White Spot. And Neptune has a number of moons around it that we're not going to explore today, but we will see the orbit of its largest one here, of Triton. Triton was the first world that we observed evidence of cryovolcanism on back in 1989 with the Voyager 2 flyby. One of the neat things about its orbit is that it is retrograde, it's backwards. And that's actually part of the proof that this is a captured object. It didn't start off around Neptune. It was really a small planet out there, like Pluto, all by itself, but ultimately was captured by the gravitational forces of this large ice giant. Let's go ahead now and take a brief view of the Uranian system. As we approach Uranus, we will see the orbits of some of its moons that also, for us geologists, are small planets. And one of the most striking things about the Uranian system, of course, is that it looks like a bullseye laying on its side. And as we kind of sweep around and look back toward the center of our solar system, toward the sun, we notice that that bullseye is tipped over, directed back at the sun. And we believe that this is a consequence of Uranus being struck by something, large collision early in its history, tipping it over almost completely 90 degrees to the plane of the other planets. And it must have done that after it already had these moons or small planets going around it, because they also have shifted over and formed that bullseye pattern. One of there are a number of moons there, including Miranda, Ariel, Umbriel, Oberon. These are named mostly for characters of William Shakespeare, but a few, like Umbriel, are named for characters from the author T.S. Eliot. Now let's take a view over to everybody's favorite planet. We mentioned before, and looking at the night sky, you can see in the early evening off to the southeast, and that is Uranus. Uranus has a lot of moons, or excuse me, over to Saturn. Pardon. Saturn. Saturn has a very large number of moons, but you're not going to see them with the telescopes you have. These are found by very large and very large ground-based scopes and some space-based scopes. So that now we have, I believe the latest count is 174 moons officially around Saturn. But 7 of them are special. They are those that are in hydrostatic equilibrium and differentiated. And so you really have 7 small planets that are traveling around Saturn. You see their orbits here, including out at the edge here, Iapetus, and we'll take a look here at Saturn's rings. And we kind of can fly right through them here with our open space program. But now we're going to, we'll come back here and go over to Enceladus. And as we will notice, Enceladus is very, very close to the outer rings. And we believe that something happening on Enceladus is actually responsible for some of the outermost material in those rings. As we look here at the surface, we see some large craters, but other regions that look very fresh, indicating that some geologic processes have operated recently or even possibly ongoing here on the surface. And near its southern pole, we see some interesting fractures, faults, some tectonics going on that looks very much like the pattern you see on our mid-ocean ridges here on Earth, with extension and transform faults. And the Cassini spacecraft one day was passing by Enceladus, looking at this southern region, and looked back toward the sun and saw, illuminated by the sunlight, icy particles that were shooting out through ice geysers above the surface. And those, again, these are cryovolcanoes, but the cryovolcanoes here were just constantly spewing out huge amounts of water, along with some hydrocarbons and other things that make us think that there might possibly be a liquid ocean of material, or at least a slush, underneath this ice shell that could actually contain microbial life. We don't know that, but we know that the chemistry is right. And so there are plans in the future to try to send space probes here for the purpose of looking at those molecules to see if there's any evidence of existing or even ancient life on this world. I'll make a brief stop at Titan. We'll look at Titan in future shows, but Titan is the second largest moon in our solar system, and it's actually larger than the planet Mercury. And it's special because it has a thick atmosphere. Now, we're looking through that atmosphere in this view with radar from the Cassini mission. But as we look at the surface, what you're seeing is dark in radar are smooth areas, and the bright areas are high and rugged. So it looks like there's sort of a large lake or maybe a small sea here around the equator. But we actually landed a probe called the Huygens probe at the surface and found out that there's no liquid here, but these do look like low-lying lake beds and stream channels. We actually see things that look like branching, or what we call dendritic stream patterns that lead down into this dark plain. And we believe that at times this has liquid in it, but it doesn't last very long because it very quickly at the equator evaporates and goes back into forming the thick atmosphere, largely of nitrogen, about 96% nitrogen, but then about 4% methane. No oxygen here in the air. But that methane in particular is at the right conditions at the Titan temperatures to act like water here. It can exist as a solid, a liquid, and a gas. So it basically evaporates, forms clouds. The clouds form and then they precipitate. They rain and snow back to the surface, and then they evaporate and start the process all over again. So rather than water cycle, there's a methane cycle, or what we might call a methanologic cycle rather than a hydrologic cycle. But at the poles, things are a little different. At the poles of Titan, the temperatures are colder. And so when we see these dark spots at the poles, we actually have evidence now that these are not dried up lake beds. These are actually filled with liquid, but again, not water, liquid methane. So now we're going to hop over to our largest planet, Jupiter. For a while, a few years ago, it got to claim that it had the most moons as well. But then astronomers started finding more and more and more at Saturn, so it lost its privilege there. But Jupiter still has 95 moons. There will be more found, so that number will go up. Not sure that it'll ever will eclipse Saturn, though. But of course, Jupiter doesn't care because it has most of the mass of all of our planetary family. Between the Sun and Jupiter, that really is the mass of our solar system, and everything else, including Saturn, really is sort of insignificant. We don't think it's insignificant, of course, because we live on one of those planets, but Jupiter is enormous. Its mass is incredible, and you're seeing imagery here from the Juno spacecraft showing you the wonderful cloud bands and many of the cyclone storms here that churn in the atmosphere. Now, most of this world, like our other gas giants, is hydrogen, but that's invisible. What you're seeing are the frozen ice crystals of compounds like ammonia, giving you these sort of yellowish clouds. The reds and browns are compounds like cyanide. And some of the wispy whites might actually be little crystals of H2O, water. We're going to pull away from Jupiter here and look at 4 of those 95 moons. And we will, I'll show you their orbits here. And those are called the Galilean moons or satellites. And just like before, these are special in that they're really small planets. And today I'm just going to concentrate on one of those, and that is the ice world Europa. And as we zoom into Europa, if you're a science fiction fan, you may know that Europa is sort of a centerpiece of Arthur C. Clarke's 2001: A Space Odyssey and the sequel 2010. This is sort of where the aliens hang out, where the monoliths will originate. And as we head down to the surface, we see a icy shell with ridges here that are very similar to ridges we see on Enceladus, where we have eruptions of those ice volcanoes. So it's been proposed that these also may have had plumes erupting from them. And we actually have evidence both from the Galileo spacecraft reanalyzing those data, as well as some imagery from the Hubble Space Telescope that, in fact, these are erupting in places. So because we also have good evidence that there is a very thick or deep ocean with more water in it than all of Earth's oceans combined, underneath this ice shell, we're also hopeful that this may be a place that there existing microbial life. But how do we search for it? Well, we may send spacecraft equipped to fly through those plumes of material. But to sort of survey out what we need to do in the future, we have a spacecraft on its way right now called Europa Clipper. Clipper will arrive in 2030 to map out the geology of this world in detail and start those investigations, really the planning phase of where we need to look and how we need to look for any evidence of life on this ice world. So now I'm going to come into our main asteroid belt and take a look at the largest occupant of that region, which is a small planet too called Ceres. There are actually 4 small planets that hang out in our main asteroid belt: Ceres, Vesta, Hygeia, and Pallas. And as we approach here, we're probably just going to see a spherical object, and I'm going to have to show you how to turn on the imagery here. Right, so this defaults to just showing you that, hey, there's a round thing there. But as we go over here to scenes, we can go to layers and color layers, and we'll add in the detail from the Dawn spacecraft that went out and orbited Ceres for a while. And here we see a lot of craters here in the ice. You notice that they have this, they almost look like these sort of diffuse lakes, and sort of sagging of impact craters is a good indication that this is an icy surface. And also we see evidence that there is some sort of liquid, or at least the slushy material beneath the surface. There are cryovolcanoes here, including the shield volcano, the shield ice volcano called the Huna Mons. And it shows up like a kind of a pimple here on the surface. But we see evidence in some of these craters of very bright salt materials. And they're in shadow right now. This is the actual shadowing you would see from the sunlight out in our solar system right now, if you could travel out to those distances. And so we're going to finish up here. I'm going to go through our inner solar system very fast this morning. And in future presentations, hopefully we'll have things worked out so that this will air over on Southern Space Rocks, and you can join us there. But again, this will be posted there later. Let's take a quick look here at our red planet Mars with its two moons, Phobos and Deimos. These are actually captured asteroids. They are not small planets. They're sort of lumpy potatoes. There's a thought actually that Deimos could actually be formed much like our moon did, with something hitting Mars and throwing material out, and then it forming back into a moon. But it's still, that moon took on the shape of asteroids, as sort of a lumpy potato rather than a sphere. But here's a real color image of Mars, and you see many craters here. You see a large impact basin here, the Hellas Basin, and right in this area is where the rover Perseverance is, here on the edge of Isidis Planitia. And we can again come up to the pole here and see that the ice and the ice caps. This ice is largely water ice, sort of with an armoring of dry ice or carbon dioxide ice right at the surface. And again, we'll go quickly through these this morning. We'll come into our next into our Earth-Moon system. Again, I encourage you to go out and look at the moon. This is a great time to look at the moon as it's in its waxing gibbous phase up to first quarter. The contrast and shadowing on many of the craters on the lunar disk is at its best. And here we see that this is the side that faces us, the near side. And that means that the other part illuminated right now, as it approaches first quarter, is one half of the far side, and that we don't get to see without spacecraft. We see the ancient highlands here, composed largely of the rock anorthosite. And then we see the dark material filling some of these basins are eruptions of lavas, of basaltic lavas, most of that occurring between about 2 billion and about 3.8 billion years ago. Let's take a look then at our sister planet, Venus. Venus has a thick carbon dioxide atmosphere, so thick in fact that you would be crushed if you were underneath it at the surface of Venus. But that thick blanket of carbon dioxide also creates an extreme greenhouse effect, making the surface of Venus the hottest of our planetary neighbors on a solid surface. And we can only look through the dense clouds with radar like we did at Titan. And when we do that, we see incredible features, including some impact craters, but also giant areas of deformation where we believe there's upwelling warm material underneath. We see some impact structures, but we also see a lot of volcanoes. So here's, you see the difference here. This is an impact structure that actually had flow-like ejecta coming out from around it. We also see some special volcanoes here. Here's something that's called a pancake dome that we think may be thicker, more silicic lavas, kind of like rhyolite or obsidian domes here on Earth. We don't know the compositions. We hope we will learn that in future missions. Here's a whole field of those domes. But we also see giant basaltic shield volcanoes that would be much like Hawaii here on Earth. And this is one of those areas where there's a large shield and then these huge lava flows that go out great distances because, again, the surface is so hot that it takes a while for lavas to cool off. So they are allowed to be very fluid over very great distances. And then we'll finish up this morning with Mercury. Mercury's surface temperature is actually cooler than the maximums on Venus. It's only about, Venus gets up to near 500 degrees Celsius, nearly 800 degrees Fahrenheit. Mercury only comes in at about 425 degrees on the sunlit side. So Mercury does rotate around, so its different parts are bathed in sun at different times. And on the daytime side, it gets up at the equator at around 425 degrees. But you cross over the terminus into the shadows, and it drops down to around minus 180. So there's just an extreme difference there in temperatures. And as we look at the surface, people compare it to the moon, but it's not very much like the moon at all, quite frankly. It's heavily cratered. But instead of seeing those giant basins filled with later lava flows, most of the lavas here are forming the crust that you see. And there's evidence of giant flood basalts that flowed out here very early in its history, close to 4.5 billion years ago. Very, very fluid lavas that actually could get carved into portions of the original crust, actually eroded the rocks like flowing rivers, but of lava. And so then later craters on top of that. So that's where I'm going to end this morning. Again, sorry for the technical difficulty, and hope you were able to join me, or would be able to join me in the recorded version later. Feel free to ask any questions, and you're also welcome to email southernspacerocks@gmail.com if you have any questions or comments. We'd love to hear from you. And thank you very much for joining us. We will be back here next week with another version of our at-home planetarium show. And in coming weeks, we will go back to the format I used when I did this in the pandemic, and we'll start to have guests that will join us to talk about different aspects of our solar system and our galaxy and even beyond, with both my planetary science and astronomy friends. And again, I thank you for being here with me. I hope you have a